Hello, everybody. Welcome back to week 2 of Informatics 109. So this week is all about hardware, the physical components that make up the computer. We're just going to look at a different section. Hardware mostly corresponds to the IT support degree program. So no matter which one of the programs you're going into, you're not going to get away from the hardware because we're working with the hardware. But IT support would be the one where you have class after class after class and taking things apart, putting them back together, and really learning all of the hardware components in and out. A quick announcement: on Thursday, for those coming to campus, there would be more we're going to do hands-on stuff. It's hardware, right? We learn by doing it. I've taught this a vocabulary class before, so there's going to be some words and quick definitions written on the board, but that's really going to be used as a checklist. So when we start opening up different machines, make sure we can check off all of those major components and all the different types. So hands-on stuff this week. And on Thursday, there's an annual event. Ivy Tech does every summer. It's a kids' college, bringing a bunch of elementary school kids, I think like 3rd to 6th grade age, and hopefully inspire them to an educational pathway early, get them interested in science and learning and knowledge and all of that stuff young, so that it progresses through to encourage kids to come. So they're going to be here, and y'all know what our society's like. Everybody gets really, really cautious if we're putting 50 kids in a public building these days. So the doors will be a little bit different. When the security protocols here change, we're in the east wing of Ogle Hall. They only keep one door unlocked for Ogle Hall, because obviously we can get anywhere in the building. And the one they keep unlocked is number 1, which is over by the Chancellor Suite. So on the west wing, the side that faces the faculty and staff parking lot, that's the one that will be unlocked. I was told that there's going to be a security guard standing by the door here. So right out here by the community room, the auditorium, probably right beside where you all parked in the back parking lot, the closest parking lot here. They said the security guard will be there letting people in and out. So you can come there and there'll be somebody to let you in, but the doors will be locked. So you might just, I guess, kind of like knock on the door. And they don't want people just knocking on any door. So they said, please come to the one by the auditorium. So yeah, at the end of the east wing here, out in the back parking lot, the security guard's going to stand there to let people in, and door number 1 will be unlocked, so you can go up and over the archway and come right down the stairs and sort of bypass all the area where the little kids are that way too, because the little kids are going to be in the hallway here. So if you come right down come in the front door, go across the archway, and come down the stairs, you're almost walking straight into our computer lab. I think everybody understands that, right? If we're putting 50 kids in one place, modern world, it leaves people worried at times. It won't really impact our class other than that. We have some hands-on stuff to do. Yeah, I brought a bunch of stuff. We're probably on Thursday looking at microcontrollers and single board computers. I really think that's the future of computing. Instead of buying the device that you can, desktop or laptop, and adjusting your needs to work with that device, we make the exact system we need when we need it. We just, instead of buying the finished component or buying the finished product, we buy the components and put it together to perfectly fit our needs. Very, very easy things to work with, very nice. I'm a little more familiar with microcontrollers. I like those a lot better. A microcontroller is basically a chip. The ones we will work with they're already soldered onto a PCB with a bunch of connections that the engineer thought we would find useful, but it's just a reprogrammable chip, and it runs one program. It takes one script and it just runs that over and over and over and over again until you cut power. I like those. There's also single board computers like Raspberry Pi, are the cheapest ones. We have a bunch of those in the closet. Up to like NVIDIA Jetsons. If you like Windows, Latte Panda would be the single board computer that runs Windows. There's lots of them, but it's basically a motherboard and a whole bunch of things the connections we're familiar with, and then along with what's called general purpose in and out pins. And that's basically what we have on a microcontroller, is just a chip with a whole bunch of general purpose in and out pins. They can be used for whatever we want to use them for, and we just solder whatever wires we have there. There's little plugs that kind of fit on them, or just alligator clamps, somehow connect a wire to those pins, and we just control the voltage going in and out, which is actually very, very easy because it's a binary level at that point. It's either on or not. And think about the symbols. If we write out binary code ones and zeros, 2 symbols is not enough to do anything complicated with. So when you get into working with that stuff, the only hard part is how we notate it, trying to make sense of all of the long strings of ones and zeros, which we are going to see next week. Start building some understanding of that. But I really think those things are the future of computing. Instead of buying a device and adjusting our needs so that we buy the component to build the exact device we need when we need it. There's George. I kind of knew we could be on the Zoom call. I have other announcements on there. So yeah, hardware stuff this week. Oh no, the audio is on. Hi George. So this week's about hardware. So a bunch of time in the class today, we're going to be taking apart some machines. I will set up a camera so y'all can see what's going on. And we got microphones and speakers in the classroom, so your classmates be able to hear you and discuss and stuff. So yeah, hardware is a little bit different on a Zoom call because all you can do is really just look at it. But like everything, it takes a little bit of practice, and to practice with hardware, you don't need the latest, fanciest computer. Actually, if the goal is to take it apart and put it back together, you probably don't want the latest, fanciest computer, because that's a lot of money to spend on something that you just want to take apart and put together. An old computer that barely works anymore will be fine for adjusting things like seeing how, a great example is how hard do you push the RAM chips in? Set those people off at first. Obviously it's a breakable piece, but it's plastic, so it's somewhat flexible, but it seems flimsy. And especially at first, you have to push a little harder than what people would expect. To start to feel it. So you want to get some practice with things like that with hardware. Got some other stuff. I might as well talk about this now. Before we get into our list and the hardware stuff. Is there anybody that's heading down the IT support program pathway, or just really interested in hardware? Or this might just pique your curiosity. It could just work for if you've ever been. Zoom buttons are in the way. There we go. I had to wait for Zoom button. I am not a fan of disappearing buttons. If anybody's heading towards a software development pathway, disappearing buttons are awful. I'll say that now. When you make your software someday, and Zoom's worse than some of them. Some of them, they disappear and come back in the same spot. Zoom buttons disappear and come back in a different spot, so you have to look for them every single time. But I'm going to search for this bin eater 8-bit computer. It's a YouTube channel. Hello. This is probably the first video on it.
Protect my business from cyber threats. To help with advanced.
Is the sound coming through the Zoom call? Sorry if so. I guess we don't really need the sound.
Security Comcast business. It's not just awesome, it's happening.
Get started with fast speeds and advanced security for $49.99 a month for 12 months.
I'm gonna play with
Today to learn more.
bin eater.
You may be young. I'm everywhere now. In time, you'll go first.
There we go. So the difference between an 8-bit computer and a 64-bit computer is just more of the same thing. We don't change anything. There's no conceptual change between them. We just have 8 times as many wires. So he sat down and
So ever since I uploaded a few videos of this,
He builds one from scratch. So it's like 44 videos here. Yeah, 44 videos. The last one is definitely the longest. I probably, without that 45-minute video at the end, they are all like 15 to 20-minute videos. I guess there's some that are 30 minutes, but they're not very long. But also he talks really slow, so I pretty much watched all this stuff at like double speed and was still able to follow along and understand him. But he builds this whole thing from scratch, goes over the concepts, what he's doing, talks about what he's doing at the electrical level, and goes through the whole process of building that through those videos. So if you're interested in hardware, I'll send this playlist out and an announcement after class. Actually, I could put it. I can do that now. Where's the overall playlist? Okay. And I will send this out on an announcement. If you're interested in that, it might just, if you're really interested in hardware, or you just satisfy some curiosity of what's going on with the computer. Just like when he's building the clock, he talks about how the clock interacts with other pieces and the control units. When he's programming the ROM chip, the electric ROM chip, which is read-only memory, but we actually have a reprogrammable ROM. We have since the early 1980s. Reprogrammable ROM is like, you have to take special steps, but he explains what's going on, why he's programming certain things, why he's doing that, how it's all set up. And it's kind of an interesting thing to see. A couple people also commented that they were seeing files when they logged onto the lab computer, so they might not be frozen this summer. I said they were frozen, so every startup was like a new startup. But we did get all brand new computers in both labs. So when a couple people pointed out that they didn't seem to be frozen and they were seeing other files and stuff, I suspect he didn't freeze them this summer because they're all brand new and there's probably some little adjustments that he made. A lot of times they're frozen, but if you see a file somebody else up on that computer, you're on like the guest account, don't worry about that. Whenever you log in, set up in your own account and log in, then you'll only see stuff you left on there. And if they're not frozen, you'll be able to see the files you left on there. I'm going to put neat videos. Here's a playlist of the guy doing an 8-bit computer completely from scratch. If you're interested, I would say not a requirement, but there's probably some things about computers' internal workings you might be curious about. And when he's going through those videos, definitely explains them. So that is there in the announcements, but it's kind of neat to watch. So yeah, he builds the whole thing from scratch, talks about every step along the way, very, very detailed and thorough. So I would highly recommend watching it, but it is 44 videos long. So stretch it out. Right? Just put it on your list of things to watch occasionally. And I had no trouble at all following along at double speed. He does talk pretty slow, so you might actually want to increase the speed no matter what. But I always had it at 2x speed and was still able to follow along fine. But it's something I found interesting. I like to share with people just if you want to see it, because that's not something many people do. And to scale that up to a 64-bit computer is just more of the same thing. He has another playlist where he makes a video card from scratch. It's not a nice video card. He loads in a picture of a carrot, and it's oh man, it looks like an Atari game once it's loaded in. But he builds the video card from scratch and explains the process the whole way through. All the stuff that's going on. Kind of a neat thing to watch. to see what's going on and maybe answer some curious points you were curious about. Some of the things that are current in the modern world are completely happening inside of that silicon, so all we can see is a little black box. Which, by the way, the black box isn't silicon. Black is just because that color dissipates heat really well. If you ever cut one open, inside of those little black chips, there's it's like purplish, kind of purplish clear. So glass is also made of silicon. So that's the closest. So the chip silicon isn't like the plastic that we see coating it. The silicon is actually closer to the glass in a window, but it doesn't have any carbon in it, so it's not quite as clear as glass. A little bit smoky and kind of purple colored. That's what actually does everything. But electricity flows through it, so it gets hot. We have to dissipate heat. That's one of the main pieces on my list, way to cool it down. And putting it in black plastic, anybody who's ever rode in a white car and a black car in the middle of summer knows the difference that a color makes. Or stood next to a white car or a black car in a parking lot. The color makes a big difference. That's why the chips are surrounded, the silicon surrounded in black plastic. Helps protect it, obviously. Hardware. So the introductory level class, just kind of talking about things, getting a broad view of it. Remember that survey aspect, looking at the different, throughout this semester, we're going to look at all the different pieces of the School of IT, make sure you're in the right program, make sure you're in the one that really interests you, catch your interest, and that you really, really enjoy. So the hardware is the physical components making up the device, the electrical devices. So the tool that does all this stuff, though, it does seem a little bit wrong to just say the tool, because without the software that we'll get to in a couple weeks, the tool is kind of useless. We need a way to translate between machine level and human level. We'll see that next week. But the physical components, there's a few of them that are very important. We want to make sure we know. I made a list of 10 things that you want to kind of be able to identify when you look at your computer. And after we talk about them for a few minutes, probably I move slow and get easily distracted sometimes, so that might go up to about break. It's not a very long list, but then we've got a couple of devices here to take apart, open up and mess around with. And I have a box with some like laptops and phones that have been taken apart in previous semesters. I haven't had a laptop or phone break since the last time I taught the class in the spring, so it hasn't been very long ago. But we at least have the other parts there we can look at and stuff. And these are the things we want to be able to identify whenever we look at a device. Make sure we know what those are if we're claiming to be computer experts. So first one on the list, central processing unit. This is where everything happens, the main part of it. I'm going to draw a picture and kind of go over it with a picture, because when we look at it in the devices, it's just a box. We know there's microscopic components inside there based off the shape, but we might not really know how they work. So there's a few main pieces, and this is introductory level, so not getting into every single detail here, but there's going to be a control unit. That is the piece that forms the connections. And that video playlist I just sent out, that Ben Eaterwing, this is, he's kind of building one of these. These are the pieces that we see there. Clock is very important, and that's not your timing clock. That's not your time clock. the, like the date and time that we see when we look at the screen. This is just a pulse to synchronize everything. Not time, synchronization pulse. So unlike a static clock, we might have a pulse that runs the next instruction. That's then another one comes up really quick. But then it's going to be really long, so it'll be a long time before we get a couple more quick pulses to activate the next signal. So not time, it just sends out a signal so that everything can synchronize. It's like it sends out the next start signal. So like start this, and then whenever that it gets a signal from the control unit that instruction is ended, it sends out the start signal to run the next instruction. So the other use of the word clock, wanted to make sure that was clear because just about every device we have also has the clock, the time clock, and we not the same thing. We just use the same word for both of them. I'll abbreviate here. Somewhere in there, there's going to be an arithmetic logic unit and a floating point unit. And these are the ones that actually do the processing. These take two different numbers, and when we're thinking about them, we're always going to think about they take two numbers and add them together. But in reality, they take two numbers and subtract them. If we need to add, we subtract the negative. The reason for that is it's kind of legacy. It still applies a little bit. But like way back in the day, if we were adding in order to do all our math and something went wrong, it would keep adding, and then the voltage would get huge voltages and it would become a fire risk. But basing all of our mathematics off addition, which you all are hopefully somewhat familiar with, back in the day could become a big fire risk. But if we base all of our addition, all of our mathematics off subtraction, and our add is that the opposite. When we subtract the negative, we get addition. But if things go wrong, we subtract and we just run out of voltages. It's not a fire risk if we base it all on subtraction. But because of how most humans think, whenever we're considering these pieces and talking about them, we're going to think about them doing the addition the way we would build up all of our mathematics instead of the subtraction. And only the electrical engineer that actually designs the chip, I guess the electrical engineer just draws a picture of it and then runs it through the machines. Only the electrical engineer needs to worry about that subtraction part. And these are almost the same. I'm going to go ahead and jump. Now that I mentioned that, I'm going to talk about adding. This adds our stuff, whether we're using actually doing math or comparing things. So we need to compare two numbers. All we got to do is subtract. If we subtract and get a 0, that means they're the same. They're equal. If we subtract and get a positive number, that means our first one was bigger. If we subtract and get a negative number, that means our second one was bigger. So all the selection stuff we would do happens there when we need to manipulate things. That's the pieces that actually do the processing. And there's two of them. We're gonna get to binary soon, but think about our number system. So like 123.45. The whole number side over here on this side of the decimal part, and when we get to binary, we'll talk about what's so wrong about calling that a decimal. It's actually called a mantissa, but nobody knows or uses that word, so we don't really need to get too far in there. But on this side of the decimal point, our columns increase going from right to left, right? We have the ones, the tens, the hundreds. And on this side, it's kind of the opposite, but everything's on the bottom, but tenths, hundreds, thousands, it's like they're increasing going left to right. So when we add things, plus 2.7, right, we go down the column, carry stuff over. The whole number part is going this way, and the fractional part is going this way. That's why there's two of them. One of them goes right to left, and the other one goes left to right. The same way our numbers, the powers increase here. It will make more sense when we get to binary next week, which is the same thing as this. We didn't invent a new way of dealing with numbers. We just use different symbols for them. So those are the ones that actually do the processing. I put a box here called registers. And actually kind of jumped to number 2 on the list because I like to overlap these on a picture. Then our RAM, which is number 2 as far as the important ones. But as far as diagramming, I like to have it overlapping a little because the CPU is useless without RAM and RAM is useless without CPU. So neither piece could do anything on their own. So it doesn't necessarily go outside of it, except that it doesn't have to be included like the other pieces. And then there'd be a large bus connecting all of these. A bus is like a wire. Oh, I want to connect that way. A bus is like a bunch of wires next to each other. So if we needed to send 8 signals, we could run 8, or however many I drew, 6. If we needed to send 6 signals, instead of setting up something on the clock so that we time how long it takes to get down one wire, we run 6 signals. Works a lot better internally, like on the motherboard, we do it from the factory. It's kind of hard to plug up the word for it would be parallel. You can see from drawing a bunch of lines, we have a bunch of parallel electrical lines. It's kind of hard to hook up. So we use like universal serial bus. A serial is one line, and we use the clock to time how long the pulses go down the wire. That's a lot easier for external stuff, but internal stuff coming from the factory, it's no problem at all to run a whole bunch of lines. Especially if all it takes to run those lines is draw a picture and then print that picture on a piece of plastic that we dip in copper. And actually, we print it on there with an ink that there's 2 ways: either repels copper from sticking to it or attracts copper to it. So then when we dip it in a liquid solution full of copper, like the one that attracts, where the ink printed is just going to attract a bunch of copper, and then we have the line. That's how circuit boards are made. So we have the big bus going through there, a bunch of lines. That's an important one. I guess I could put that on the list somewhere here too. RAM is random access memory. ROM would also be included here as our memory. It's volatile storage would be the technical term. That's the storage that only lasts until we disconnect the electricity. Whenever it'll hold stuff. Some things, at least in theory, could hold data indefinitely, as long as we don't remove electricity from it. So it's our working spot. It's a lot quicker than long-term storage, the one that would last, or the technical term is going to be non-volatile storage. And RAM and registers, both of those are our non-volatile storage. RAM holds the current program. And registers hold the current step. or we might often say current line, the current instruction. This our program is built up, made of lots of instructions, but we run those one at a time. So the control unit says it's time for the next thing. Actually, CPUs work off fetch, execute, increment. This is what that piece is doing over and over and over again. It's fetching the next instruction. So it goes to the control unit, says it's time for the next instruction. The clock synchronization tracks step. So along with the synchronization of everything happening at the same time, it continually increments like a clock. So it starts at 0, 1, 2, 3, 4, 5. So it always knows what the next step is going to be. So maybe we just ran step 5. So that finished. So control units, the clock increments to 6. That's the last one here. I wanted to start in the middle instead of starting at 0. So we just finished step 5, executing step 5. The clock increments to step 6, and when it does, the control unit moves to the next step. Looks at it, oh, clock just incremented to 6. So it comes down, grabs instruction number 6 from RAM, loads that into the registers, which this picture is a little deceptive. There's several registers. So the A register, and the B register. It's typically done like this. So maybe the next step is to add 2 numbers. Put one of the numbers in the A register, the other one in the B register. Both of those run together through the ALU and feed back into the B register. That might be getting too detailed. It's an introductory class. I don't need to go too deep down rabbit holes. So there's been a number of times I sit here and explain how a transistor works in this class and the difference between transistor and MOSFETs. And I don't mind rabbit holes. So if we start talking about something that really catches your interest, feel free to distract me down that rabbit hole. We'll still be picking up proper terminology and learning about computers and stuff. So the control unit grabs our next instruction, loads it into registers, which then the control unit will start executing that. And if we're going to do math and need a couple numbers, it's going to see that the control unit is going to see that in the registers. Like the instruction we load in is going to say load what's in bit 378 in RAM into register A. So once that's loaded in the register, the control unit will see what it needs to do next. So execute that instruction, then increment the clock. So then it goes to step 7, which in that case would be like load 215 into register B. So the control unit is going to grab what's in RAM spot 215 and stick that in register B. And then the path to the arithmetic logic unit is automatic. It's like plugging it in. It's like a plug. Once we put 2 numbers in those registers around it, we plugged it in and electricity flows through it. Y'all know how quickly plugs work, right? Your device shuts off. What's a good one in the kitchen? Coffee maker. As soon as you plug your coffee maker in, it works. You're standing by the wall and plug your coffee maker and blender in at the same time, they're both going to work. So that's how these pieces work. So they're only do one thing. And it always follows this. So the control unit fetches an instruction, loads it, which means grab it from RAM, put it in a register. It executes that instruction, then increments the clock. That order is very important. You may know why increment needs to come last. Have any thoughts on that? What would happen if we fetched the instruction, incremented our clock, and then executed the instruction? See any problems with that?
Start happening at the same time.
some of that, we could put pause breaks in. So the big problem, let me put an example instruction here. Jump to previous instruction. So repeat the instruction we just did. So we fetch maybe we fetched instruction number 5, increment our clock. So our clock now says 6. Jump to previous instruction brings us right back to 5. So we move, yes. So we move back and then we move our clock afterwards. So we're on previous instruction, we jump back to number 4, and when we increment, we should go on number 5. Did I say that right? This is what we want to happen. But if the clock already went to 6, we'd only go back to 5 over and over and over again. Sorry, I said that wrong. So maybe instruction 5 runs and we want it to run again. So we say jump back to the previous instruction. But the clock's already incremented, so it goes back to 5. And it's just going to move on again. We're not going to run. We don't run. We see step 6 again instead of step 5 again. So we want to execute that instruction in case it changes the clock. More common one might be something like jump to instruction 19, or just jump somewhere else in the code. That's where the big problems happen with it, because it throws off our orders. So we want to make sure and not get it off in the order. That's something you will see periodically of internal working of the computer that we never change. So random access. So central processing unit and that's kind of a mouthful. So we do abbreviate everything. The arithmetic logic unit, floating point unit. We're going to call those ALU, FPU. Random access memory and read-only memory, which in our modern world, we have several versions of read-only memory, usually electronically erasable, programmable read-only memory. So EEPROM. Lots of acronyms. I think everybody was probably already aware of all the acronyms coming in. I find it helpful to actually remember what the acronym stands for. Because we see so many acronyms, they start to blend together after a while. And if you remember what it stands for, then you can quickly come back up, pull out those first letters to get the acronym again, instead of more just pure blanket memorization of just trying to tie this acronym to a particular piece. The acronym is just an easier way to say it. The name usually explains what it does. Hopefully. There was a little phase where it lasted about 7-8 years. The people would come up, computer scientists were particularly bad about coming up with the acronym they wanted and then thinking of words that made that acronym. So there's quite a few of those floating around, but in general, if it's a good descriptive one, I would recommend memorizing the words, and then you can just pull out the acronym for it afterwards. What's next? So these are electronic components, take a lot of electricity, right? So we need to get that from somewhere, some sort of power supply. In America in 2023, do I need to get into details about power supplies? When you take your IT support class, you will have lots of details about power supplies, but that's like going through the data sheets for a particular power supply. Like, will this one work or this one? Right? And reading the numbers off the box, figuring out which one you need. There's a lot of that. You don't want to get the power supply wrong. If you're on a computer that requires 12 amps and you buy a power supply for 15 amps, you're gonna bring stuff up. Or if you require 12 amps and you buy a power supply that only provides 10 amps, you're not gonna have enough power to run it. So that's just lining things up, but otherwise that's where we get our power in and regulate our power. Get and regulate power. Because your regulation is very important too. Using that previous example, if we're working on a machine that requires 12 amps to come into it, we don't mean somewhere between 10 and 14 amps. We mean 12 amps. Or voltages. Voltage is probably a better example. Amps are current, and current is the actual flow of electricity. Just like current in the river, it's the flow of the river. That happens really, really quick with electricity. Too quick for us to do anything. So what we do is set up voltages, voltage is a potential. Something could happen. Gravity is a good example of a potential. So if we're up on like a flower pot, sitting up on a balcony, 3 stories up in the air, it has the potential to fall. It's not falling, but gravity always pulls down. So there's a potential for that to fall. And that's like what a voltage is. The potential for electricity to flow. And then some point later, a little cat comes along and pushes that flower pot off, then it's actually falling. Gravity is going to take hold and it's going straight down to the ground. That's what current is. And once it's falling, there's not much we can do with it. We can catch it on its way past, try to catch it on its way past. That's how we operate with it, but it happens too quickly for us to do anything with, so we work with the voltages. Charging a phone is a good example of that. Phone chargers all take 5 volts, and they better be exactly 5 volts. But everything in your house is putting out 110 volts. All the plugs in your house put out 110 volts. Or if you go to Europe, it's slightly different. You go to Asia, it's slightly different. All the countries have their own voltages, but here in America, it's all putting out 110 volts, which is way too much for our phones. So we need to regulate that down to a very precise measurement, because that's charging a lithium-ion battery, and those can explode. So we want to be careful with things like that, especially laptops, phones, mobile devices. Lithium-ion is a better way to make batteries, but it's also explosive. So we definitely want to make sure our power supply is set up right. One of the important parts. That's reading through your documentation and making sure all the numbers line up correctly. And it's not a situation where 3 out of 4 numbers matching is going to be okay. Everything on that list needs to match the one you're looking for. Like why it's so hard to replace a power supply from a laptop. Has anybody ever noticed that? They don't want non-computer experts doing that. They want they only want people who have passed a bunch of classes and taken the A+ certification. They don't want people who have A+ certifications handing somebody a power charger and saying this will work with your laptop. And it wouldn't be hard to stock the store shelf with them. I'm sure the stores would love it because they'd have to sell them constantly, and they'd probably end up selling a lot more computers too. But we want to restrict who can actually point to a power supply or grab a power supply off the shelf and be like, this will work with this particular laptop. So we got electricity feeding in here where we do stuff. That's one thing we know for certain about electricity. Anybody heat their house with electricity? It gets pretty hot, right? I always hear about those early computers. They say the size of a house. The computing part, well, the part that actually does stuff was never bigger than a desk, a typical office-sized desk. The radiator was the size of a house. It's really, really easy to heat things all up with electricity, like your toaster, right? Like it's really, really hot, and it's going to burn you in a couple of milliseconds. Stoves actually have regulators on them so that they don't immediately get hot. People have time to move stuff, but a toaster's enclosed, they don't regulate those. It'll leave blisters in a couple milliseconds after you turn it on. It's really easy to heat things up, but it's a lot harder to cool them down. So that's an important part, cooling system. And everybody in the class probably just thought of fancy gaming computers and liquid cooling systems and the big fancy stuff. It doesn't have to get that big. At the beginning of class, I was talking about when we look at the integrated circuits, we see a little black plastic. That black is part of a cooling system because black dissipates heat. So it doesn't have to get to the super fancy ones, but the black plastic heat sinks. Everybody know what a heat sink is? I see some nods. So we have our like little chip sitting there. And that's going to get really hot. And the only way we have to cool it off is the air going past. The air will carry some away. So we put on top of that a bunch of little metal plates. That's not going to look right. Something like that, maybe. I'll close that one up. Then we have a bunch of little metal plates, usually something like aluminum or an aluminum alloy that will pick up any heat that comes there really, really quick. So then that airflow has more surface area to move past. Just gives it a way to get us more surface area for air cooling. Fans. Radiators, liquid cooling, pump a liquid through it because liquids can hold a lot of energy. We take a lot of that heat energy and shove that into a liquid, way more than we can shove into the air. I guess removing it's a better example, like when you go to make ice cubes. It takes a long time to pull enough energy out of that water to make it freeze. Or if anybody's ever been up around Chicago in the wintertime. It's pretty mild to be that far north because winter isn't long enough to cool off the Great Lake. You get chilly right at the surface, but about 10, 15 feet down, it's the same temperature year round. Because water holds so much energy. So whenever we have heat, one of the best things we can do is pump it into a liquid instead of the air, because the liquids can hold way more energy. Or just a humid day. A humid day is always going to feel hotter because there's all the energy stuck in that water that didn't necessarily increase the temperature. Just more energy that we can notice. Some sort of cooling system. 6, long-term storage. Our hard drives, I guess, just say it that way. Non-volatile storage. So RAM is our working storage. That's RAM and registers. That's step-by-step, program by program. This is RAM will lose whatever it's storing when power is cut off. This is it'll keep the data around for after the when the power's cut off. These days, pretty much all SSDs. Really, the hard drives, the disk drives that remain just haven't been replaced yet. Like we just replaced all of the ones in our GRE labs, not just here, all the Ivy Techs across the state. It came time to do that, and School of IT gets the new computers, and we'll have those for a couple of years, and then they'll migrate over to the other computer labs around Ivy Tech, and we'll get newer ones. So the ones that were in here still had disk drives. So like those are going over to other computer labs and instructor stations and classrooms, not just here at Sellersburg, but at every Ivy Tech campus. That's something that gets replaced at a statewide level. So those are still around, but they're already on the replacement list. Whenever it rolls back around for the next replacement in the GRE labs, then our new computers that have solid state drives will go out and then the school will probably be out of, won't have many of them left. So they're being replaced. There's a long transition. So the early ones, the reel-to-reel tape machines, everybody's seen those in movies or maybe audio tape. Some people like the audio tape. So there's this tape going by, and really that's Scotch tape filled with iron dust, iron shavings. And it rolls past two magnets. I'm going to exaggerate it in the picture. So like one magnet is on a spring and another magnet that's held stiff. Obviously in the working components, that's for the diagram. In the working components, we would use the same magnet. But the one that's on a spring, because of the attraction and repulsion between magnets, however the iron shavings in between two pieces of Scotch tape are oriented, is going to cause that magnet to bounce up and down. So that's our reading the data that's stored there. And if we use the stiff magnet, that's going to and alternate the polarity on it. That's going to change the little iron shavings or powder that's shoved inside of that plastic. So that's how we write that. So that's some of the early form. The spinning disc were very similar. It would just kind of go in a circle. So we'd have magnetic stuff, so like north and south poles, kind of going around some sort of binary state. Eventually, we would probably represent that with ones and zeros by the time we got over to the software where humans are actually working with it. But the magnetic polarity, we'd set different little blocks up for that. And again, we'd have I'll draw it as a couple of magnets. We'd have one magnet held stiff to change that polarity, or another magnet on a spring so that it would bounce up and down in response to that polarity. And that's our read and write was the same there. Disc. CDs, DVDs, Blu-ray, they used light instead of magnets, the reflection of light. So on the disc, we would have a really shiny disc, and then we burn spots on it so that it doesn't reflect. So at first, everything reflects. It's like a super bright mirror. And then we go in and burn little spots. So those spots we burn no longer reflect light, and the spots we didn't burn do reflect light.
When you burn a disc, it's actually burning.
Yes. Yes. And then, then we have, instead of magnets, we have a laser pointer. I don't really know how to draw a laser. I'll just write laser. A laser pointer and optical receiver. Something that would receive that. So we shine the laser down on it. Shine the laser down on it, and if it reflects back up, we know it's an empty spot, a spot we didn't burn. And if it doesn't reflect, if we don't get anything in our receiver, we know that it's a thing. And again, in the picture, they would be the same. So you think of it like a laser pointer, and then that top cap that sits on it, the laser shines right through the middle. Laser shining right through the middle, and that top cap has the receiver, so it's reflecting straight back up. And then just a stronger laser to actually burn it. We need to store it, just do the same thing with the stronger laser. Solid state drives are a little different. Solid state drives rely on quantum mechanics. So we have some ionized things. So in some spots, we have some extra electrons. And somewhere else, we just have a grid that's not ionized. And if we set up the conditions just right, the electrons will disappear from here and reappear over here. Am I still on the board? Okay, yeah. So it's kind of, quantum mechanics is really strange to talk about. Newtonian mechanics is nice to somebody sat there and thought about the theories they wanted to make and then found math that supported them. Quantum mechanics, they went in blind, took measurements of the universe, and then put those measurements into equations. They have never failed a prediction, but if we try to talk about it, it gets strange. Because electrons were here, and if we adjust the conditions just right, they'll be here. We know that's an absolute certainty. They're never anywhere in between. They never travel between the two. They just go to a different spot. But planes have solid state drives on them. So we are confident about that confident enough about that math equation that we risk lives on it, and we don't even consider that risking a life. Quantum mechanics is odd if you talk about it, but we know with absolute certainty it's correct. It's a math equation that has never failed a prediction, and nobody expects it. There is very little expectations that it ever will fail a prediction. It's just a math equation. I'm a fan of that just calculate. If you try to talk about it, you start to get odd stuff that doesn't make any sense. But if you punch the numbers in a calculator, you get accuracy about the universe. That's kind of what's going on with the solid state drive. They will wear out eventually. It has to do with the certain sizes. Like if we had trying to shove things into a tube, only certain things would fit. Like a wave that size would fit. Wave that went up and down, and that one would fit as long as the start and end points could match back up. If we had this wave, that one wouldn't fit. So it's based on that we know only certain options will actually work. It's called Fowler-Nordheim tunneling, but that's getting into advanced math more than that. So just our electrons jump from one spot to another, and we just flash the correct conditions to get them there. That's where the name flash drive is kind of faded out of usage, because that's where that came from. We just said we controlled those conditions, and we would just activate those conditions on and off. Then we can just activate those conditions again. Those electrons disappear from over here and reappear over here. Is how solid state drives work. Similar storage things. These two are very similar. We just went from the tape to a disk thing that we had better control over. CDs were kind of similar, and to a disk, only we switched to light and whether it reflects or not. Solid state drives are completely different. But that's we have lots of options. For this level class, we just need to be able to identify which one's a hard drive. It really doesn't matter what kind of hard drive it is, as long as we can look at the device and figure out which piece is the hard drive. If the hard drive is what's gone bad on it, and we have to replace it. What else do I have on the list? I'm going to erase these pictures here. Those were just talking about that. Sort of a little sidestep that making sure you hear all the details in it and stuff. And this is a vocabulary list. I gotta do something to make it more interesting than listing the definitions. Because there are days this semester that that's all we can do. One of the cybersecurity days will be like that. There's not much we can do other than list the definitions. The other cybersecurity day will is actually going to do some stuff like at least write simple versions of the attacks so you can see what they're like, or run simple versions on my own computer. So you can kind of see what's going on with those. Seventh piece we always want to identify is the motherboard. That is the connector for all the components. So a PCB or SMT, PCB is printed circuit board. That's the ones I was talking about where we draw a picture and then we go to print it on a piece of plastic. I have one. This is sort of how I use microcontrollers for coming up with designs, and then just order one from a factory. So this was from a game controller I made that had normal joysticks and buttons, and then I included a sliding potentiometer like we would see in an audio mixing board, and then a turning potentiometer. So there was also something, a control that slid back and forth and a turning thing. But all I did is draw the picture and send that off to a factory. And they have this green plastic, and they took that picture I drew and printed it on here with special ink, and that particular factory used a tracking one. There's also like a silk screen on there as well, so look at the backside. They printed it on there. I guess the light's all coming through. There we go. Kind of only see the front one side there. And that picture was printed with an ink that would attract copper. So they print it on there, and then they dip it in the solution, and copper sticks where the ink is. I also have another version where they print it on there and where it'll repel copper, and that kind of covers the whole thing. But the copper doesn't. It kind of gives a negative, and then they do an extra step and use that as like a print. But it just prints that diagram on there, and we have all those little lines and places to connect the things. So PCB usually refers to ones like these where there's holes going through it, and we would solder the other components on. Something big enough that it can be worked with human fingers. We don't always have that anymore. When we look at Raspberry Pis and think more computers or microcontrollers on Thursday, that's one of the things. We have a bunch of pieces that are just way bigger than they need to be, so we can work with them with our fingers and test our designs. And then we order one with little bitty pieces. So those little bitty ones is like surface mount technology. That's SMT, where we have all those pieces that are way too small for a human to deal with. So we just, again, it's built from a picture, and then after making the printed circuit board, another machine just stamps all the components into place. That's how we get the really small ones. For those boards, the main, I guess we could, it's what we would colloquially call a circuit board. The big piece of green plastic, which green is just easy on the human eyes. That's one of the most prevalent colors in nature. So our eyes don't get tired looking at green stuff the way it does at yellow and orange and some of the other colors. Right? You're looking at something really bright. You've seen circuit boards from the 70s, they were sort of a yellowish color. That's the material, what the material is on its own, but it really, really hurt people's eyes to spend like even a whole day working on a circuit board staring at something like that. So green is just a better color for our eyes, but you can order them in whatever color you want. They don't make it in the natural color anymore. They did choose options of yellow and red that aren't as bad for the human eye, but as that natural yellow. But that green board that all the pieces solder onto or plug into, that connects everything together. And for us, this is a vocabulary class. We just need to be able to identify this list of things when we open up the computer. Tower, the case for it. I'm going to write this because I know it's on your quiz this week. the form factor. So the ones I have pulled out here, the tower is just standalone piece. I assume everybody has seen a computer tower before, right? So that's the form factor. The form, the shape is in. The one that holds that all the stuff goes into. Trying to come up with words that doesn't sound like connect to. The one that holds all the pieces. The server we're going to take apart is a rack space. So it's like 1.5 inches thick, 19 inches wide. That's standardized, and then it has different depth. It has to, because it has to be 1.5 inches thick or 1.5 inches tall and 19 inches wide, because that's the size of our racks. The laptop is a clamshell. Opens and closes like a clam. Tablet's like a slate. It's like a little flat piece of slate rock. The shape it takes. Gotta have some sort of that, because if you're repairing stuff, that's an important aspect, right? Down to the details. I use my laptops. There's I think that's a 14-inch laptop and 11-inch laptop. So if you're fixing something on the case, the pieces for an 11-inch laptop might not work on the 14-inch. So all the little details in that. Towers in the most extreme examples, especially on big custom builds, people have really gotten fancy with those and bought custom pieces. Put fish tanks in the liquid cooling system and use water instead of some fancy chemical. All sorts of neat things. So that's kind of a big deal. But when you get to IT support, is another one that you would, like the power supply, you would look up every detail on the thing, and you're not going to match 3 out of 4 numbers. That's not going to cut it. Everything on the list has to match when you're replacing the pieces. Primary output. Primary input, that's 9 and 10 on the list. For the longest time, that was going to be the monitor and keyboard and mouse. That is changing as we get into IoT stuff. My go-to examples on IoT stuff is like the coffee maker. Automate your coffee maker so when you're heading home, you can hit a button on your phone, and then the coffee's ready when you get home. Coffee's ready when you get home instead of having to wait 10 more minutes if it's been a long, exhausting day or something. In that case, the coffee maker would be the primary output, and your phone is the primary input, or actually the database that both of them connect to would be the primary input. But the thing about it is simplify it here. So the phone's the input and the coffee maker's output. The other example I always go to for IoT provided stuff, that's what we're going to talk about Thursday. It's like put a scale on the refrigerator shelf, so that if that scale detects the weight is really low and your phone GPS reports that you're at the grocery store, your refrigerator will remind you to grab milk. Like, there's not much milk left here. You might want to remember to get that. And in that case, the refrigerator shelf is the primary input and your phone's the primary output. So it is, those last 2 things on the list are kind of nice with IoT stuff taking over, because we have more interesting examples than keyboard and mouse for the input and monitor for the output. But whatever you're getting your input from and wherever the output's going. And number 10 here is actually probably I'm most familiar with microcontrollers. That's one of my favorite little hobbies to do on the weekend, is try to design new input devices. That's fun. Some of them work better than others. Waving a paintbrush around in the air to control graphic software. Hardware worked, software worked. The core idea was a little off. It worked if I put a canvas in front of me and then had that reference point of like the traditional art easel and the canvas sitting on it. But waving the paintbrush around completely free was too many degrees of freedom to control computer graphics. a motion capture suit to control a synthesizer. It seems to be working. I'm not a very good dancer. I'm not a good enough dancer to test it. But get all the synthesizer controls from actually dancing instead of just tapping on keys or something. But sit around and make different inputs or outputs. A water feature, like a water is going to fall on its own, so all we got to do is open and close gates at the right time. And computers can get really, really good at opening and closing things at the right time. And gravity doesn't change, or gravity does change. Gravity doesn't change enough at the surface of Earth that we would have to worry about that. It would happen slowly, and then the whole time in a minute would go with it. Like when Jupiter came around the same side of the sun as us, there'd be less gravity, but it would affect everything. So keeping the same timing, all the waterfall would still happen at the same time, and just open and close gates so that like looks like a 7-segment display as it falls. Old alarm clock style. Make the waterfall like that. That's really, really fun stuff to do. I really enjoy it. And there's kind of no limit. That's where the stuff we're going to look at on Thursday with single board computers and the microcontrollers really, really shines, is inventing new things to fit a particular need or something that might be interesting. Obviously, for the general purposes of introduction to your School of IT program, the correct answer on the quiz for primary input is probably still going to be keyboard and mouse. Primary output is probably going to be the monitor. Maybe the printer, if the quiz has been around for a long time, like say a printer, but something like that. Yeah, how we interact with it, how we interface with the computer. That's going to be an important word in IT. So that's all the pieces. The main pieces, that's definitely not all of the pieces. That's all the pieces we're going to look at today. So looks like it's a good time for a break. And I was thinking after the break, I got a tower here and a server, and I have a phone I took apart last semester, and took the phone apart 2 semesters ago when I taught the class last fall. And in the spring when I taught the classes, we took apart an old laptop of mine, so we can kind of compare them, pull those boards out, get our hands on, do some stuff. But first, maybe a break. 10 minutes sound good to everybody? Got big heading out here in the classroom. So it's 2:13. We will get back to it at 2:23. See y'all in just a moment.